So I remind everybody we covered linear programming, basically we started to speak about linear programming. We had the diet problem at which we were given a few half planes. There might be some from above, some from below. About notation, when I'm drawing a line, it means a line. When I'm drawing a line with little fair on one side of the line, I mean the half plane that is bounded by this line and contains all the points which are on the fairy side of this line in all the drawing. And here we are giving a set of half planes that was in the diet problem. Every vitamin defines a half plane, namely all the diets that you can tolerate. And then we had the cost function, C1x plus C2y was a cost. C1 and C2 were given constants. And what they imply are that I can look at the vector whose coordinates are C1 and C2. Look at this vector. I can take my stick, put it orthogonal to this line, orthogonal to this vector, and now start shifting my line parallel to itself. That is, if you remember, all the affordable diets were all below this line, and as I increased my budget, this line contains more and more points, more and more diets, until at some point it hits one of the vertices, not necessarily the lowermost one, depending on what's the direction of the vector. I hit one of these vertices, and I said, now I have somewhere in the feasible region. Feasible region was all the diets that I get enough much vitamins, and in addition, I can afford it given this budget. All the points along the line all have the same budget, all cost the same. So among all of them, I looked for the points that was the best. Okay, let's talk about linear programming geometry. So each constraint defines a half space. What is half space? Half space might be in 2 dimensions, just a half plane. In 3 dimensions, if I'm looking at the constraint AI vector x vector smaller or equal than BI, A is a vector given to me, BI is a constant given to me, and I'm looking at all the vectors, points x. In 2D, it just boils down to AI, 1 x plus AI, 2 y is smaller or equal than BI. That's how it looks like in 2 dimensions. If I had 3 types of food and wanted to solve the diet, then the only change here would be plus AI3 of Z, for example, and still smaller or equal than B. Much easier in vector E when I'm using vectors, dot products. Everybody here is cool with dot products between vectors? Or you want me to remind you the basic definition? Okay. So that would be a half space. That is, if I'm changing it with an equal size instead of small or equal, then I'm getting some plane in 3D. And the half space are all the points on one side of this plane. In 4 dimensions, I have hyper planes or hyper spaces, but for not making it even harder to pronounce, we'll still call them half spaces instead of hyper space. Okay, so in linear programming, each constraint defines a half space, some region in the d-dimensional space. It is a convex. We talked about it. The same if you have 2 points inside the half space, then the segment connecting them is inside this half space. The feasible region is intersection of convex objects, hence it's convex, and a intersection of half spaces. And in the 2-dimensional plane, there is one example of such constraint. Here is another example of such constraint. Now, because that would mean that, for example, you have to get at least some amount of vitamin I. That would mean that you should not consume too much of vitamin I. You can always take this type of constraint and make it into this type by multiply both sides by -1. But what happens when you multiply both sides by -1? Then the direction of the inequality switch. A colleague of mine calls them the direction of the equation and the direction of the inequation switches. So what can we say about the intersection? It could be open to its intersection of several half planes, as we said. All the points here. This is your feasible region. These are diets that you can afford. From all the points in this region, you want to pick the best point, the one with the minimum price. And what hopefully I was able to show you is that there is always the solution to the linear programming first is a point in the feasible region that is extreme in the direction of the target function. Extreme in the direction of the target function. Let's see if I get it accessible, otherwise I wouldn't spend time on it. It's not. Here, that in this example that I massaged in the meantime. That in this example that we played with last time, I can change the direction of the cost of an orange. I can change the direction of the cost of a banana. Let's put both of them quite high. and this vector is a target vector that has these two costs as its parameter, and the region of all the points that I can afford as I increased my budget. This line of all the points that I can afford, that I can afford are only here, and keeping this vector when I'm increasing this budget. My region increases, but the orientation of the line, just determined by the ratio of the two prices. To change the orientation of the line, I just need to change this orientation. That was a feasible region. The intersection, if you remember, of the 4 vitamins for half planes. Each one defines a region of its own. That's where the healthy diet, and the point that I was after was, as I'm slowly increasing my budget, what would be the first vertex that my budget can hit? Okay, so our theorem stated that our theorem is that any bounded linear programming, because it might be that my solution is infinity, but any bounded linear programming that is feasible, that it has any solution, because sometimes you don't have a solution. I can give you 3 half planes, 1, 2, 3, and I'll ask you what is the intersection of this region, intersection with this intersection with region, intersection with this region. So far, here is my intersection of these two, intersection with this guy that limits you to be below it, and now there is no feasible solution. It's not clear that with all your constraints, it intersects. The same way that with a diet problem, I could have phrased that instead of optimizing the diet, instead of just asking find the cheapest diet that I can afford, remind you, these are the region of all the diets that are healthy enough. This line and below are all the diets. They are all the diets that I can afford. I can phrase it as an optimization problem, or I can just ask, what are the diets that with a budget of $30 I can afford? And now it's not optimization problem, it's a problem of asking, is a feasible region of this half planes, everything that I can afford, intersection with everything that is healthy, is this empty or not for my given budget. So now it's linear programming where I just care for answer yes or no, feasibility region is empty or not. So, solution for the linear programming is a point in the feasible region, and if it has a solution, then there is also it's not necessarily unique, but you can always find a solution which is a vertex in any dimension. Why? Let's see it in 2 dimensions. Here is my feasible region. Proof by example, here is my feasible region. I'll start moving, say, I'm trying to find the lowermost point. Let's say that I'm going down. By going down, I'm improving my cost function until I hit one half planes. Following it, I'll hit another vertex. Following it until I'll hit another vertex. And when I'll get stuck, it will be because I reached a vertex, intersection of two. As long as I'm inside on an edge, there should be a direction that will either keep the cost function the same or will improve my cost function. In either way, it's linear function. If for one direction it increases your cost, then in the other direction it decreases your cost. So you can always continue for the direction that improves your cost until you hit a vertex. And the same goes for higher dimension. You can always move until you hit a face, then move along the face until you hit an edge, then move along the edge until you hit a vertex. Now, I'm not claiming that this solution will always be that the solution will always be a vertex. It will only be a vertex. It could be, as we said, that the feasible solution is empty. It could be unbounded. Here, if I'm looking for the minimum, I'll find this point. If I'm looking for the maximum, I'll find infinity. Or it could be that it's not unique. I'm looking for the lowermost point. That's my cost function. Just look for the minimized y value. But you see a lot of points over here with the same y value. But all I'm saying is that either this vertex or this vertex will give me the same value as internal point in this case. So it's okay to limit our search space, to move our search space from all the points that lives in the feasible region, all the infinitely many points, into only vertices of the feasible region. Okay. How do you solve linear programming in higher dimension? The simplex algorithm, it's a basic algorithm with many, many variants. One of the huge amount of works about the simplex. Very well, very used, very, very popular. How does the simplex algorithm works in higher dimension? Let's talk about the feasible region in 2D. Feasible region in 2D. I have half planes. All these half planes defines a region, a polygon, which is convex, right? Here is my intersection of all these half planes. It's a polygon, convex polygon. How many edges does it have if I have n half planes? How many edges, how many vertices do I have? It's the same number in a convex polygon. N is almost correct. Yes. Another one of my half planes. It's pretty much correct, but it's at most n. Here is a half plane that doesn't contribute an edge. Here is a half plane that contribute an edge, but at most one edge. Okay? So I can compute it in n log n. I can compute this intersection, and I'm kind of okay in 2D. In 3D, I can still create the feasible region explicitly. That is, in 2D, one possible algorithm would be generate all the vertices of the feasible region and check the cost of each one of them. Right? Here, I can generate each one of the vertices of the feasible region, even though we'll see a better algorithm, and evaluate each one of them against a cost function. 3D, you can kind of still get away with this approach. Higher dimension, an attempt to build all the vertices of the feasible region, if you have n half spaces, might have a complexity which is n to the power of d half. Okay, so good luck to do it with thousands of constraints and 20 dimensions. D half, 1,000 to the 10, it's a lot. So how comes that the simplex algorithm works so well is that it doesn't attempt to build all the vertices. It works by starting on, now my box is an intersection of half spaces, in 3D. I'll start by picking a vertex, do kind of a steepest descent, hitting an edge. Let's say that I'm trying to get to the lowermost point. Hitting an edge, follow this edge until you hit another vertex, pick another edge that is in your favorite direction, try to go down along this edge until you are getting to a vertex that you cannot improve anymore. And because of all the convexity, local minima is also a global minima. In convex shape, if you get to a point that you cannot improve anymore, you get to a local minimum, this must be a global minimum as well, as opposed to non-convex where you still might have plenty of other minima. So simplex works by kind of greedy steepest descent when you just follow edges of the polytope that lives there in higher dimension. Polytope is the intersection of half spaces. Okay, so what we are going to do, we'll see how much we'll finish today, is discuss the algorithm in linear dimensions, incremental randomized algorithm in linear dimensions, and then talk about applications to problems like network flow of linear programming and integer linear programming. So just the linear programming now is with vector notation. In higher dimension is here is a diet problem, but now I have D types of food: bananas, oranges, avocados, yada yada. So what I'm looking for my variable is a vector x, x1 dot xd. These are how many units of vitamin I am I eating per day. My constraints are, somebody gave me a vector AI, where each component tells me how many units of vitamin I have in each type of food from bananas all the way to food D. In vector notation, it would be AI vector given times x, my variable vector that I need to find should be larger or equal than bi. These will be my constraints, and bi was also given a constant. C is the cost, C without vector, is the cost of a unit of food, Cj is the cost of a unit of food j, and the vector C now is just this vector of cost, and you are trying to minimize the cost of C dot product x, given, but such that for each one of the vitamins, AI dot product x should be at least bi. Okay, that would be the general linear programming. If you like matrices, you can take the vectors I can take the vector A1, A2 vector, all the way up to AN vector, and multiply by the vector X, and want this product to be small or equal than the vector B. Just a shorthand, larger or equal, to be consistent. Larger or equal than the vector B, even a shorter notation. Okay, very quick glance about the history for the sake of time. Sorry for being late today. I got slightly different version about where exactly it was solved. If it was during World War II or immediately after, but the immediate application of the simplex algorithm was apparently for solving transportation problems of which airplanes take which cargo. So that was the main motivation. Back to Danzig. But I also heard versions that it happens during World War II, so I'm not sure. But it's in some worst case yet, this algorithm is exponential. So even not in practice, it's hard to find such an examples, and the examples where the simplex is exponential vanishes the moment that you introduce just tiny bit of noise to the parts. They are very, very unstable, worst case example. In practice, simplex is great. There were lots of attempts to give a strongly polynomial algorithm that always runs in polynomial time. There are algorithms that run in pseudo-polynomial parts. There is the ellipsoid method that, what's cool about the ellipsoid method was that we were able to extend it now to problems that comes with the COVID and runs in much higher dimensions, and it's still, ellipsoid method can work on multiple convex programming problems that are not linear. What about going back down to lower dimensions? Can you find in 2 dimensions, can I solve linear programming in linear time? Yeah, Nimrod Megiddo gave a really, really complicated algorithm that runs in linear time in any fixed dimension. And this algorithm really puts theoretician in somehow strange light because it runs in linear time in any fixed dimension. But if you look at the dependency on the dimension, now dimension is how many types of foods do you have. This dependency of the dimension is 2 to the d to the power 2 to the d squared. Okay, so it's really, really working for very, very small distances and very hard to implement. I'm going to show you a linear time algorithm that runs extremely fast and way easier to understand instead of the deterministic one. Actually, it's not for you. You don't have to solve it in n log n time, but if you want the highlight of how can you solve it in n log n time, what essentially you're doing is you think about 2 subsets of half planes. There is one subset defines as a convex polygon. I'm using many half planes. They defined their intersections, their polygons that I already computed. It's convex, and I store it actually in sorted order of vertices, so I can kind of sweep it or visit all the vertices going from left to right. That was with one half of the half planes. And I'll take another such polygon that I created from the other set of n half planes. And if I computed this creature and I computed this creature, that is, what I did so far was to split my set of half planes into 2 subsets. I see that people already go seeing where I'm going to. I took all my half planes, divided into 2 sets. I compute the feasible region of the first half. I compute the feasible region of the second half of half planes, and what would be the fixable region of all the half planes. It will just be these intersections of two convex polygons, which I can do in linear time. Compute this region of the intersection of both. Now, how do I compute the intersection of each piece separately of the first half, n half, and the second n half? It's of course divide and conquer. So it behaves kind of like merge sort. Split and then merge them together in linear time, so it's n again. But I want to get into linear algorithm, and it will be linear in higher dimensions, and it will use some of the ideas that we rehashed in the last weeks. Faster algorithm in smaller dimension. Let's start from a linear programming in one dimension. Linear programming in one dimension. It is now all I have is a half line. I'll only have a half, not a half space, not a half plane, a half line. Everything that happens is on this line. What will be my constraints? I will be given a set of constants alpha 1 to alpha n, set of constants beta I, not necessarily in a sorted order, and I want in linear time to find the minimum x such that x is larger from every alpha I, and x is smaller than every beta j. Help? How can you do it in linear time?
By having pointers on.
They are not sorted.
Finding the max alpha.
Let's look at all these values. I'm looking for an x which is larger than all the alpha i's and smaller from all the beta j's. So I think that that's what you meant, to hold the pointer to the maximum.
Yeah, to hold a pointer to the alpha 3 and beta 2, and if I found a solution, like if there is a solution, then it's okay. If I'm not finding the solution, I'm shrinking my window.
I think that I understand, but so what we are doing is we are looking for a solution that is larger from all the alpha i's, smaller than all the beta j's. So out of all the alpha i's, who is really matter? The largest one. That is, among of the smaller values, I'm looking for the largest one. Among the large values, the beta j's, I'm looking for the smaller one. Right? Because if x is larger than every alpha I, then x in particular is larger than the largest alpha I. So I just need to find the maximum and the minimum of each set separately. Find the maximum and the minimum of each set separately, and then my x are the fixable region of all the x's in this region that lives here in between. And oh, by the way, it is quite possible that here is the way that my alpha i's and beta j's are arranged. In which case, I don't have a solution at all. This algorithm will tell me there is no solution because the minimum is smaller than the maximum. So I tell you that there is no solution. Okay, here is exactly the same problem. Aiming for an algorithm in 2D. Here is the same problem of finding a solution on the line, except that now we have many more notations. And what I'm going to solve and get used to this notation is I'm going to solve the one-dimensional linear programming, but now I replace the x-axis from the previous slide with some line L. I'm saying I'm only looking for solutions that must be on this line L, not half plane, line. Only look for solutions that are on the line L, but in addition, other parts of the input are the half planes H1, H2, all the way up to HL. So I'm only looking for points on L, the highlighted line, which are smaller than some half planes and larger than other half planes. Obviously, it's the other way around. Or in other words, I'm looking for the intersection of all these half planes, not algorithmically, conceptually. I'm looking at the intersection of all these half planes, and I'm looking for a point that must be in this intersection, but must also be on the line L. And I want to convince you that that is exactly the problem that you saw one slide ago, just with many more notations. Why is this the same problem? Because here is the algorithm. Let's assume that I don't have any half plane that is completely vertical. The line is completely vertical. Everybody has slight tilt, maybe minuscule tilt to either clockwise or counterclockwise, which means that every half plane either contains this point. What is this point? The point with x equals 0 and y equal infinity. If I go high enough, maybe my half planes will contain this point. And if it doesn't contain this point and it's not vertical, then it must contain this point in minus infinity. Okay. Each half plane I can characterize into one of these two classes. Okay, so let's consider only half planes from the first class. Only the ones that contain the point y equal infinity, the very high point. Here are all my half planes. Let's compute their intersection of the planes that define them with this input line. Remember, I'm looking for solutions just on this line only. Let's take the first half plane of this type, compute its intersection points with L. And I'll do the same for H2 and H3. These were the open parentheses from the previous slide, and now I'm looking for a solution that finds the highest point among these three, the maximum point among these three. What it defines, that's a maximum value. You can think about it as it shoots a ray, if you want, from this maximum value upward. My solution, as far as these half planes are concerned, my solution must be anywhere along this way, starting from the highest, the maximum value. Remember in the previous slide, we looked at the maximum of the small value, doing exactly the same for the other half planes that I erased temporarily. I'm doing exactly the same trick with the one that looks downward. Compute the intersection point with L. Look at the minimum value of these intersection points. And if you want, you're shooting away from the smallest point, now downward. What's your feasible region? The part of L here in between. All I did from the previous slide to this slide was that in the previous slide the line was horizontal and now I rotated it somehow. But everything else is exactly the same, just more letters, more notations. Everybody is good that I can solve it in linear time by just finding the maximum and minimum of all these points? I mean, maybe it's worth mentioning a half plane that is given as, I'm sure that you know it, but I'll say it nevertheless. If I have ax plus b y is smaller or equal than c, and I have a line L specified whichever way you want, then you can find the intersection point of this line with the line ax plus b1 equals to c, which is a line as well. And I hope that you know how to find intersection points of two lines. Okay, that's my feasible region. And oh, by the way, just as in the previous slide, I can also discover in the same way that the intersection, that the feasible region on this line is empty. The same example from here, just rotate it a bit. Right, that Q min is smaller than P max. Okay. Here is an order n square incremental algorithm for solving the IRP. I'll increase the half-lengths one after the other, insert the half-lengths one after the other, and every time that I'll add a half-plane, I'll check what was the previous optimal solution that I had before adding this one new half-plane, and is the optimal solution agrees with the new half-plane. If it does, great, I don't need to change it. If it's not broken, don't fix it. If the new half-planes does not, if the new half-planes violate the old solution, then I need to do something. I need to fix it somehow. That would be the general idea. Increase the half-lengths one by one, and we're already kind of similar to the approach that we had with finding the closest point. Adding the points one by one, now I'm adding half-lengths. A few notations. Age I is the ith half-planes, age for half-planes. Li is a line that bounds age I. Every half-planes, its boundary is one with the line. Okay. Ci is a feasible region of the first I half-planes. That is, look at the age 1, age 2, all the way up to age I. Look at the intersection. And Ci is the feasible regions of intersection if these are the only half-planes that I have in mind. From 1 up to I. Generally, I'm going to go all the way up to n, but at the moment, I'm at the I step, so I'm only looking at the first I half-planes. Now, big warning, I'm not going to compute Ci at each iteration. I will never care about what are all the vertices of Ci or all the edges of Ci. But conceptually, it still exists. It's just the intersection. When I move to the I plus 1 step, I just say that Ci was changed by adding intersection with one more half-plane. Okay, get Ci. Vi is something that I am going to compute for I equal 2, 3, 4, 5, for every I as I'm adding half-planes. What is Vi? It's the optimal solution for the first I constraints. That is the best solution in Ci. So just to see that people feel comfortable with the notation, I'll draw something and you'll tell me what is Vi. Again, I'm drawing something, you'll tell me what is Vi. And to decide about the cost function, I'll use this cost function. C of xy is just y. There is no limitation of generality. You can always rotate your half-planes. So your cost function is just pointing vertically down. That is, my cost function ignores x completely. H1, H2. Where is V2? Yeah, V2. Correct? These are my half-planes. I'm looking for the lowest point that is on the correct side of both half planes. The feasible region is everything inside of this wedge. This will be the lowermost point. Everybody good with this notation? That's V2. Where is V3?
Still V2.
Sorry?
It says still V2.
It's the same point. Well, this is also V3. Let's add edge 4. Somebody else?
V4.
Where is V4?
Yeah, no, same.
I'm sorry?
Same.
It's still the very same point. Right? How do I know? Because V2 doesn't violate edge 4. Obviously, if I have an optimum solution and I have a new constraint that doesn't violate, but the previous solution agrees with the new constraint, then I cannot find a point that is better than this one, because it was the best point even before. So that is also V4. A little bit more. Page 5. Sorry, V5.
Still the same.
It's the intersection of
Intersection of H5 and H2.
I know that I need to change V2 because it doesn't agree with the previous solution. H5 violates V2. And you see already something interesting. The new solution must be actually on H5. Maybe it's an accident, so it's just on V5. And indeed, V5 is this point. Then no solution. I don't have any solution. Okay. Everybody is good with all the notations? Yeah. You have it also on the slide. Here is C3. Again, I'm saying we don't keep it explicitly. We just know that it exists. And here is a vertex V3. Okay. This is both a theorem, but it will also dictate our algorithm, etc. As I said, I'm going to go add half planes one by one. If Vi minus 1 is inside Hi, does not violate Hi, then what will be the new optimal solution is just the previous optimal solution. And what's even cooler, to check if this condition is satisfied, what do I need to do? I have Vi, some xi, yi. I have the half planes given, say, in this notation. Just put xi here, yi here, and see if it's satisfied or not. So it's constant amount of work. Right. If, on the other hand, Vi violates Hi, then, as we'll see, you do need to look for a new solution. Vi minus 1 will not do. So we have a new linear programming problem to solve. But there is some catch that will help us a lot. Beforehand, I was looking for a solution in the whole space, in the whole two-dimensional plane. Sorry. Every point in the two-dimensional plane might have been a candidate. This theorem stated that if Vi minus 1 is not on Hi, then Vi must be, of course it's inside Hi, but it argues more. It's on the line that bounds Hi. You just need to look at a one-dimensional space now instead of two-dimensional space. And that will make all the difference in the world. So when I look at the new solution, I will have to check only the line that bounds Hi. Just to make sure everybody remembers notation. This is Hi, everything here, and this line is Li. And the conclusion would be, if you don't find a new solution on Li, then there is no solution at all. The feasible region is empty. And it's important that we first check the first condition. When I'm adding a half length, like the case of adding H3, I definitely could not say that the new solution must be on L3, if you remember. But why? Because V2 did not violate H3. Only if H3 or H5 in this case violated the previous solution, only then I'm sure that the new solution will be there on its boundary. So this statement is true only if this statement, if I check this statement, this doesn't work. Okay. So why do you see the picture of a cat here? It's because I like to ask people the following question. Here is the Earth. This is the equator. I'm putting a rope around the Earth, thinking about it as a completely concentric circle. I've seen the equator, completely nice metal ring surrounding the Earth. It has some circumstances, some perimeter, and now I'm taking a rope and putting it around the equator. Good Google question. And now I'm taking another shred of 6 feet. I'm adding it to the shred, rearrange it, cause circularity around the Earth, still. They are concentric, and asking if there is a room for a cat to walk between the equator and this new ring that I arranged. And your immediate answer is absolutely not, because the 6 feet are completely minuscule compared to the size of the Earth. I think that everybody that is asked, unless I'm giving you time to write the equations, it's kind of the requested answer, though it's completely minuscule. A way to understand what's actually going on is to think about the relationship between R and the perimeter. It's 2 pi R, etc., but all it carries is that the perimeter versus the radius is a linear function. And what can I say about linear function? Let's look at some value, delta x. Let's look for this linear function at this difference, delta y. And because it's linear, then as long as I keep delta x fixed and move x, but delta x is fixed, delta y will be the same. Put x anywhere, but if this is 1, then look at what is delta y. It will be the same no matter where is x. So the fact that the Earth is relatively large is completely irrelevant here. I could have do the same experiment with a tennis ball. Take the tennis ball and then add 6 feet and arrange it concentrically, which will actually 6 feet divided by 2 pi gives you 1 feet, which is far enough for any mountain lion, I think. So definitely. So, but the takeaway message here is that for linear function, if you move a bit and it improves your cost function, then if you keep going in the same direction, you'll keep getting the same improvements in this linear function. As opposed to convex to quadratic function, that it might go down and then might go up again. It doesn't happen in linear functions. Why is this relevant for us? So, here is the old solution, VI. It's in the intersection of all the half planes, not including HI. HI, this half plane. Here is VI minus 1, and I'm adding HI. The old solution is violated. Where is a new solution? Let's assume by contradiction that, well, it must be in HI. It must be in the intersection of all the previous half planes, because it's the optimal solution of everybody. But by contradiction, it is not on Li. It's somewhere in the interior of the half plane. Let's connect a segment between Vi minus 1, previous opt, to the new opt. And now let's start walking along this segment. First, all the points along this segment are inside Ci minus 1, what I said beforehand, or Ci minus 1. Which one of the two solutions are better, cost function-wise? Obviously the previous one. The more constraints that you're getting, the more expensive it becomes. So Vi is better, Vi minus 1 is better than Vi. My cost function is linear, implying that as I'm moving along this segment, my cost function is becoming better and better. Keeps changing in the same direction, right again. Okay? Because cost value at Vi minus 1 is better for me than cost value at Vi, and the change between them is linear, implying that this point is in HI, this point is not in HI. Walking along this segment, at some point I must exit from VI, from HI. This whole segment is inside Ci minus 1. Why? This whole segment is inside Ci minus 1. Why? Convexity. Ci is convex. Definition for every 2 points, segment is inside. Walking along this segment, there is a point which satisfies everything and is better than Vi. Conclusion, Q, a point which is on Li, is better than the point that floats somewhere in the interior of HI. Conclusion, if you added HI and it violates Vi minus 1, you can just go and look for solutions on Li itself, not floating in the whole 2D world of HI, only on the 1D problem, on Li itself. Okay. And obviously, if you don't find the solution on Li itself, then there is no solution at all. The intersection of the half planes is empty. Okay, so from now on, I'm looking for solution on Li itself in this case. So let's see how the algorithm looks now. As before, Ci, it's the intersection of the half planes, but compute actually it should be C2, the intersection of H1 and H2. You don't really need it, but you definitely want V2, which is the best point in the intersection of these two half planes. Okay, so you have V2 for the first two half planes. And now I start adding half planes one by one. And for every half plane HI that I add, if Vi minus 1 is inside this half plane, then do nothing. Vi is just Vi minus 1. It takes you constant time to check it. Same way that when I added a point, it took me a constant time going the closest pair to check if the distance was changed or not. Else, that is, else Vi minus 1 violates HI, then Vi must be on Li. How do I find it? I'm calling the one-dimensional linear programming that we see a few slides ago with which parameters? H1 dot Hi minus 1 and a solution that must be on Li, the line that bounds Vi. Okay, and that's essentially the whole algorithm. So we just need to check its running time. That will be my solution. But of course, I call this 1DLP. 1DLP told me one of the two things. Either it said there is no solution on Li itself, and then you're saying, okay, then there is no solution at all. Or if there is a solution, then Vi, the new optimal solution, is just a solution that the 1DLP told you about. And the running time, just as in the adding points, could be n squared. Why? Because it could be that every new half planes violate the previous solution that I had earlier. But so it could be that the running time is 1 plus 2 plus 3 plus 4 plus. Every time I need to call the 1DLP. So that would be the worst case. How can we improve the worst case? Like, what did we do in the case of the adding points? Or maintaining the maximum. How can we improve the same?
Just randomly add constraints.
Take a random permutation of the half planes. Take a random permutation of the half planes. Add them by a random permutation. Excellent. If I'm doing it, I'm looking at the I step. I just added age I. What's the probability that when I'm adding age I need to call the 1DLP? 1DLP is expensive. Checking if the old solution works is cheap. What's the chance that I added the 1DLP? And we'll stop in this argument. How many half planes define the new optimal solution? Yeah. Yeah, but how many of the optimal solution? What happens if my first half plane is this guy, my second half plane is this guy, and every other half plane is added later? That's the best solution. I compute, this is V2 and it doesn't violate anybody. In general, how many half planes define the optimal solution in 2D? 2. 3D? 3. So there are two special half planes. Remember this picture? That we had this set of balls. We had this set of balls, and two of them were special. Before that, it was the two closest pairs. Now the special are the two half planes. If I told you what is the half plane, and then asking you what is the optimum, the order of insertion doesn't matter. The optimum doesn't depend on the order. And there are two half planes that define the order. If this is the last half planes that I added, then I need to compute a 1DLP for everybody, because the previous solution must disagree with this half plane. If this was added as the last one, then again, in the last iteration, I need to call the 1DLP. If among these half planes, I pick anybody that is not one of the two red ones, then it doesn't violate the previous solution that I had, and it takes constant time. So out of this I half planes, what is the probability that I'm calling the 1DLP at the I step? Exactly the probability that I need to do the rehashing when I look at the closest point, 2 over I. Same argument, there are two special elements. What makes them special, I don't care. But only two special elements will cause me to call the 1DLP, and in every other case, I don't need to call the 1DLP. So I have a much better chance that I don't need to call the 1DLP. So the expected time per operation is what? If I need to call the 1DLP, it takes me I time to call the 1DLP, but the chance that I need to do it is only 2 over I, so these two i's kills each other, and I'm left with expected work of constant per iteration. So the expected running time of this algorithm is again linear. The same gymnastics that we did for the closure spell. Okay, we'll talk next meeting. I thought that we'll do it today. For next meeting, we'll talk about for a few more minutes, we'll talk about the 3D LP. And then we'll switch into various applications, especially network flows that I think that is really cool and much easier to solve with linear programming versus other way. We'll talk about vertex cover, approximation algorithm for vertex cover, approximation using linear programming, relaxation. I think it's going to be quite cool. Okay, thanks everybody. Jack, maybe I'll give you a little optional, a little MATLAB, something to do with ILP that requires just call the simplex algorithm and understand what the answers mean. Okay, thanks.
So in this slide, should this vector be negative C instead of C? Right?
Yes.
Okay. We just want to make sure. Thank you.